Be going over the 2016 AP Calculus exam. Number 1 is a graphing calculator problem. It says water is pumped into a tank at a rate modeled by W of t equals 2,000 e to the negative t squared over 20 liters per hour for time 0 to 8, where t is measured in hours. Water is also removed from the tank at a rate modeled by R of t in liters per hour, where R is differentiable and decreasing on 0 to 8. Selected values of R of t are shown in the table above. At time t equals 0, there are 50,000 liters of water in the tank. So this is an initial value that's going to help us later on in the problem. A lot of times we'll have some kind of differential equation where this will allow us to solve for C, but in this case we'll be using it with the fundamental theorem of calculus. So part A says estimate R prime of 2. So if I'm finding R prime of 2, I know that R is located in my table, and my units are liters per hour. And if I want at time 2, I notice that I have two values that are on each side of 2. Okay, so all I do is I find the slope using those 2 points. So my 2 points are 1, 1190 and 3, 950. Okay, so if I'm estimating R prime of 2, I do this by doing R of 3 minus R of 1 all over 3 minus 1, which is those values. So it's 950 minus 1190 all over 2. And this works out to be negative 120. Now my units on the top were R, and R is in liters per hour. And the units on the bottom was time, and that was in hours. So we have liters per hour. So our final units are liters per square hours. So liters per hour squared. Part B says use a left Riemann sum with the 4 subintervals indicated in the table to estimate the total amount of water removed from the tank during the 8 hours. So if we're doing a left Riemann sum, you could do a sketch where you try to perfectly draw out every single point. A lot of times calculus teachers will just talk about drawing a certain curve and not worrying about where those points are and just putting random points in there. It doesn't matter to me. You can do either. We do know that this is a decreasing function, which is going to be handy on the second part, which says, is this an overestimate or underestimate? Now, personally, I don't draw a graph at all, but I do know that I'm on the interval for the first 8 hours, 0 to 8, and I have certain time amounts that are given to me. I have 1, 3, 6, and 8. So I typically draw like a little, something like this. So 1, 3, 6, and 8. And then I write their heights above it. So R of t at time 0 is 1340. I have 1190, 950, 740, and 700. So if I'm doing left-hand endpoints, I'm using all the values that are on the left. So imagine you have some kind of decreasing function. You're doing the left and over, left and over, left and over, like that. So I'm going to use the heights of 1340, 1190, 950, and 740, and I end up not using that 700 because it's a left-hand endpoints. And the widths here are 1, 2, 3, and 2. So that's like saying the first rectangle is 1 unit wide, the second one is 2 units wide, and so on. So I have 1 times 1340, I have 2 times 1190, I have 3 times 950, and I have 2 times 740. And this is what I call my left Riemann sum with 4 subintervals. So often in class I was writing it as L of 4. You don't need the L of 4, but what you do need are products and sums. So you need some kind of product, like your width times height for each of those rectangles, and you need to add them all together. So if you work this out using your calculator, you get that this is 8,050 liters. All right, so we now decide whether it's an overestimate or an underestimate, and we're giving a reason for our answer. So our reason is that this ends up being an overestimate. So you can see from my sketch here that these rectangles go over because I knew I had a decreasing function, right? So we're going to write that. So we're going to say our approximation is an overestimate, and the only justification we need, estimate, because R of t is decreasing. So decreasing functions will have left Riemann sums that are overestimates, and if it asks for a right Riemann sum, it would be an underestimate. All right, the next problem, so C, it says use your answer from part B to find an estimate for the total amount of water in the tank to the nearest liter at the end of 8 hours. So we're trying to find the total amount of water in the tank, and if you remember from our problem, it talks about water coming in and water coming out. So water is being pumped into the tank, but water is also leaving the tank at a certain amount. Okay, and we started with a certain amount of water in the tank too. So let's put this all together. So our amount of water, so let's say let A equal amount of water. So our A, we start with our 50,000 liters of water that was in the tank to begin with. And then we're adding a certain amount. And that was the function that talked about the water coming into the tank. So if we're talking about over the first, at the end of 8 hours, we want to actually integrate that from 0 to 8. And you can just put W of t dt. So don't try to get fancy and write your function, which was 2,000 e to the negative t squared over 20, because sometimes you're stressed, and on the test maybe you forget that negative, or you write a 200 or something instead. So write W of t dt. And then we're also losing a certain amount. So if you go back up here and look, it says that water is removed from the tank at a rate modeled by R of t, where R is differentiable and decreasing on 0 to 8. Well, we just found the estimate for the amount that was removed from the tank during those first 8 hours. We found an estimate of 8,050 liters. So we're subtracting out that 8,050. And that represents our amount. So putting that all together, we can use our calculator for this portion. It's the first time I've used the calculator. Usually when it's the calculator section, we would go ahead and, as soon as we see that function, we put it in for y1. So for y1, we're going to put our 2,000 function. So 2,000 e to the negative, we can use x squared divided by 20. You can put that in, and that way if we need to find any intersection points, it's already in for y1. But in this case, we're doing the integral, so I'm going to do math 9. So yours might show up as an actual integral. And then I'm going to do vars, y vars, function y1, and I'm going to go from 0 to 8. Okay, so I get 7,836.195. And I put that together with my 50,000 minus my 8050, and then I round at the very, very end. So I keep that number in my calculator. And in this case, it says to the nearest liter, so at the very end, I'm going to round to the nearest liter. So I'm going to do plus 50,000 minus 8,050. So I get this, and I'm going to round to the nearest liter. So I'm going to say 49,786 liters. Okay, and our last part, part D. You go back up to the instructions. It says, for time 0 to 8, is there a time t when the rate at which the water is being pumped into the tank is the same as the rate at which the water is removed from the tank? So the rate at which the water was coming into the tank was W of t, and we want to know if it's ever the same as R of t. Okay, so this is a little bit tricky. So we want to know when W of t is equal to R of t. And all we have to do is prove that there's a place where that happens. Okay, so if you think about some of the theorems we know, the theorem we're going to need for this one is the intermediate value theorem. We're going to need to show that if I put W of t minus R of t as one function, I want to show that one of those values is above the axis and one of the values is below the axis. And since we have a continuous function, we're going to have to cross somewhere in between. Okay? So it's a little bit tricky because we don't have very many values. And we have one function, right? We have the actual function, and the other one we just have a table. So let's use what we have. We know we're on the interval 0 to 8. So let's see what happens at 0 and 8. So if I have W of 0 minus R of 0, I can find those values. W of 0, I mean, you can even find on your table. You can go to second table, but really it's pretty easy. You just plug in 0 for the function and you get 2,000, right? Because if you remember our function is 2,000, it would be 0 there. So we're going to have 2,000. And then W of 8, you can kind of scroll down, or you can make it so your table, you ask for the values. Yours should already say that. But if I have 8, I end up getting 81.524. So W of 0 is the 2,000. Let me write it up here. And R of 0 was in our chart. So if we go back up to our chart, we see that R of 0 is 1340. So we're going to have 2,000 minus 1340. So we get 660 liters. Now it doesn't matter what that amount is. Actually, it's liters per hour. It doesn't matter what that is. We just want to know that that's a positive rate. So basically the amount of water in the tank is getting bigger during this time. But if we talk about W of 8 minus R of 8, W of 8 was that 81 number, 81.524. And R of 8 up in our chart, way up here, R of 8 is 700. So if I subtract those two, I get a negative amount. I get something that's less than 0. So basically that means that at some point we had to have the amount of water coming in had to equal the amount of water going out. Those two rates had to equal each other, because at first we were gaining water. We had 660 liters per hour at time 0. But then at time 8, we had that we were losing water. Water was being pumped out faster than it was coming in. So at some point, those two rates had to be equal to each other. So what we're going to use is that intermediate value theorem. So we're going to say something like, since W of 0 minus R of 0 is greater than 0, and W of 8 minus R of 8 is less than 0, and we have this function that we've created, W of t minus R of t, it has to be a continuous function. Because we're talking about water leaving, right? We're not going to be like, oh, water leaves at 500 gallons per hour for the first hour, and then stop, and now it's going to be 300 gallons per hour for the next hour. It's not just like going at a non-continuous rate. There must be a value for t on the interval 0 to 8 such that W of t minus R of t equals 0. Or really like W of t is equal to R of t, right? That's what we're trying to prove by the intermediate value theorem. And you can just abbreviate, they'll know IVT. And that would be the solution. Okay. Question number 3 is a non-calculator question, and it says the figure above shows the graph of the piecewise linear function. For -4 to 12, the function g is defined by g of x equals the integral from 2 to x of f of t dt. So it says, does g have a relative min, max, or neither at x equals 10? So as we know, there are certain calculus keywords, and when we're asking for a relative min or max for g, we need to find where g prime is equal to 0 or undefined. We need to find the critical values. So if I'm finding g prime of x, I find the derivative of the integral from 2 to x of f of t dt, which uses the FTC, fundamental theorem of calculus. So we get f of x. The chain for this is times 1, so we don't need to write that. So g prime of x is equal to f of x, and we want to find where this is all equal to 0. Well, the graph of f is shown above, and it's crossing the x-axis in 4 different locations. So the critical values are at -2, 2, 6, and 10. So typically on these types of questions, what I had you do in class is we drew a number line, and we put those critical values on the number line with the endpoints on the end of the number line. And then we tested in g prime. And so we would test to see if g prime, which is really f of x above, is positive or negative. So we're negative between -4 and 2. We're above the axis between -2 and 2, above the axis again, below the axis, and below the axis again. Now, it's not critical that you do all of those different values, but we do want to look right here because we want to know what's happening on both sides of 10. So we're decreasing, and then we're decreasing again. So this means that we have some kind of graph where we tapered off to a slope of 0 and then went back down. So that is neither a maximum nor a minimum. Now remember, graders do not grade sign charts, so we need to write what's happening in this graph. And really all we're concerned about are the intervals from 6 to 10 and 10 to 12. So we're going to say g prime of x, which is equal to f of x, is less than 0 on 6 to 10 and 10 to 12. Therefore, there is neither a max or a min at x equals 10. And that's our justification. All right, so part B, it says, does the graph of g have a point of inflection? So a point of inflection at x equals 4 means that g double prime of x would have to change sign at x equals 4. So g double prime of x is going to be f prime of x, because as we know, g prime was equal to f of x, so we take the derivative there. We want to find where that's equal to 0, and g double prime is equal to 0 when f prime is equal to 0, or f prime is undefined. So we're finding where it's equal to 0 or it's undefined, and it would be, so what's happening at 4, that's where our f prime is undefined, right? So f prime switches from positive to negative because I have a positive slope for f and I have a negative slope for f on each side. So that means that g double prime changes sign there, right? So g double prime of x, which is equal to f prime of x, goes from positive to negative at x equals 4. Therefore, x equals 4 is a point of inflection. Because g double prime changed sign, right? So that's all we need. All right, so part C. It says find the absolute minimum value and the absolute maximum value of g on the interval -4 to 12. Justify your answers. Okay, so first of all, from finding the absolute max or min, I do need to find where I have those critical values. So we already found that, but let's write it again. So we have g prime of x, which is equal to f of x, is equal to 0 at x equals -2, 2, 6, and 10. But we also have to consider the endpoints. Okay, so I'm going to talk about the candidates test here. So if I have, let me see, what's the best way of doing this? If I have g of x, and I have my endpoints, so let's do -4 and 12 as well. And then I have -2, 2, 6, 10, and 12. That's a lot of things to check with the candidates test. Okay, so this is probably where I would, well, I guess we're finding absolute max and min, right? But I would probably consider the number line because sometimes there's things that are not maxes or mins. So let's go back up to the top here. And it's kind of a good thing that I did this negative, positive, positive, negative, negative, because I can consider what my possibilities for max and mins are. So my possibilities for max and mins are here, here, not at 2, because it goes increasing then increasing some more, 6, not at 10, and 12. So really I don't have to try the 2 and the 10. So we could cross those out. But we should probably try the other ones with this candidates test, okay? So we probably need to say something about that. So g prime of x, which is f of x, let's just say where it's positive and where it's negative. So g prime of x is greater than 0 on, and I would write those intervals. So I'd say -2 to 2, 2 to 6, and that's it. and g prime is less than 0. We want to know what's happening in that sign chart, right? So -4 to -2, 6 to 10, and 10 to 12. Okay, so let's figure out what g of -4 is. So g of -4 is the integral from 2 to -4 of f of t dt, which really is -4 to 2 of f of t dt with a negative out front. So we're finding these different areas. So up here, we have these areas of these triangles. So this triangle right here, this triangle right here, this triangle, and this triangle, we can kind of see some symmetry here. So if I have 1/2 base times height, the area of this one is going to be 2 times 4 divided by 2. So it's going to be 4. So we have 4, 4, and you can see that all of these are, so that's 8, 8, and 4. We're going to use this. So if I'm finding the integral from -4 to 2 of f of t dt, -4 to 2, these two are going to cancel out, and I'm going to be left with this. Okay, so I'm going to have 4 there. And you can write the areas of the triangles here, but I think it's fine if you just write -4, because most people can find the area of that triangle in their head, so I don't think the grader is going to be too concerned if you have that. Okay, so g of -4 is going to be -4, and then we go through the same process for each of the others. So if I find g of -2, well, that's the integral from 2 to -2 of f of t dt, which is going to be -2 to 2 f of t dt. Which if you go up here, -2 to 2 is going to be 8, so I get -8. And then 6 ends up being 8, you can find that, and 12 ends up being -4. So if I want the absolute max, I look for the highest point, which is 8. So absolute max value is 8 at x equals -6, and absolute min is -4, and this is at 2 locations. So it'd be at, actually, -8, whoops, -8 at x equals -2. I should look more carefully. All right, so that would be our answer on that one. So that's a pretty tricky one. It involves lots of integration. Okay, so the best way to think about part D, which asked on -4 to 12, find all the intervals for which g of x is less than or equal to 0, is to think about this candidates test that we did up here. So I would probably go through several of them and maybe put in those other critical values. So the ones we crossed out before, I think we got to find them still. So I have -4, -2, 2, 6, 10, and 12. And I really just want to go one thing at a time. And I don't even just want to do that. I think I want to put every 2 units, because I think the best way to do this is to think about these 4, 4, 4s that we're adding in, and then think about what each one is. So maybe I'll write part D up here. So we know that g of -4 was equal to -4. We found that in the candidates test in part C. So if I'm going to g of -2, what I'm doing is I'm adding in this negative integral right here, okay, which was 4 units. So it's going to be -4 plus a -4, which gives me -8. All right, and then if I go to g of 0, now I'm adding in a positive 1. So I'm back at -4. And then g of 2 adds in another positive 1. So I'm going to be back at 0. And then that's where the turning point is, right? So we're saying, where is it less than 0? Well, it's going to be less than 0 on, so g of x is less than 0 on -4 to 2. And then now it's at 0. Well, let's do one thing at a time again. So g of 4, and you could really even find g of 3, right? But g of 4 is going to be adding on another one of these 4s. So it's going to be 4. And then g of 6 is going to be adding on another 4, so 8. and g of 8 is going to be now subtracting a 4, so we're back to 4. G of 10 is going to be subtracting another 4, so we're back to 0. So it's greater than 0 from 2 to 10, and then if you notice, g of 12 is back to negative 4. So like as would g of 10.1 or whatever, it's going to be negative as well. So we're going to say g of x is less than 0, not only on that negative 4 to 2, but also on 10 to 12. And I think that's the best way of doing that problem, which seems like a weird way, but really you're just kind of thinking through every single step there. So you're doing one thing at a time and putting it all together. All right, number 4 is the classic separable differential equation. So we've had lots of practice with these. So it says on the axis provided, sketch a slope field for the given differential equation at the 6 points indicated. Okay, so looking at our denominator, we have x minus 1. So that's why we don't have any points at x values of 1, because we have undefined slopes. All right, so if x is equal to 0, then we have negative 1 on our denominator. So I'm just going to look at my y's. So this will be 0. This will also be 0, right, if y is equal to 0. The next point is 0, 1, which is going to give us 1 on top and negative 1 on the bottom. So I'm going to get a slope of negative 1. And then the 0, 2 gives us 2 squared on top, negative 1 on the bottom, so negative 4. So just make it much steeper. All right, so same thing for the other points. So I have 2, 1, which is going to be, 2, 1. So I'm going to get 1 squared over 1, which is 1. And then I have 2, 2, which gives 4 squared over 1, which is 4. So it's kind of symmetric. All right, so part B says let f of x be the particular solution to the given differential equation. Write an equation for the line tangent. So again, we don't have that word find. We don't see the word find the particular solution until part C, so don't spend a lot of time trying to solve the differential equation here. Instead, we're writing the equation for a tangent line. So we know that calculus keyword, we know that we're going to find our slope, which is going to be f prime of 2 first. So I find f of x, or I find f prime of 2, which is plugging in our 2 into this equation. Now the y value for our point was given, it was 2, 3. So we're going to have 3 squared over 2 minus 1, which is 9 over 1. So we get 9 for our slope. And we had that point 2, 3, so putting it together, we have y minus 3 equals 9 times x minus 2 is the equation of our tangent line. And I would just leave it like that so you don't make any mistakes. Now notice there's a second part of the question. It says use the equation to approximate f of 2.1. So f of 2.1 would be plugging in 2.1 into this equation. So if I plug in 2.1, I get y minus 3 equals 9 times 2.1 minus 2. This is a non-calculator question, so it should be pretty easy to do without a calculator. So I get 0.9, and then I add the 3 over, so I get 3.9. So our approximation is 3.9. All right, and then part C says find the particular solution. So this is what the ones that we have practiced so many times. So I had my differential equation, which was dy over dx equals y squared over x minus 1, and I separate. So I have 1 over x minus 1 dx, and I have 1 over y squared dy. So I've separated, and I now integrate. And just because it's 1 over something, don't always assume that it's natural log. That's what a lot of my students do that every single year. So 1 over y squared is actually y to the negative 2. So when I integrate it, I add 1 to my power and write 1 over the new power out front. So 1 over negative 1 is still negative 1. Now this side is a u substitution. My u is equal to x minus 1. My du is dx. So I do get the integral of 1 over u du. But just be careful because there are many times where the AP Calculus exam has 2x minus 1 or something. Just know that you might gain a 1/2 from your u substitution. So look for things like that on your AP test. So this one does become natural log of x minus 1 plus c. So we get natural log of the absolute value of x minus 1 plus c. Now we plug in our initial condition. So if we look back to the original problem, it said that f of 2 was equal to 3. we use that. So we plug in 2 for x, and we have 3 for y. So we get negative 1/3, and we have natural log of 1, which is 0, plus c. So we get c equals negative 1/3. So now we go back to this step, and we plug in our c value. And we slowly solve for the y, okay? So, oops, I didn't plug in my c, did I? I said I was going to. So I have negative 1/3 there. Okay, so it's a little tricky to solve this one for y because it involves a reciprocal. So what I'm going to do is I'm first going to take care of that negative. So I'm going to have 1 over y equals natural log of the absolute value of x minus 1 with a negative out front. And then I'm going to do plus 1/3. And then I'm going to take the reciprocal of both sides. So I'm going to flip this side, and I'm going to flip this side. So it's going to look really weird. So it's going to look like y equals 1 over negative natural log of the absolute value of x minus 1 plus 1/3, which we could write with 1/3 minus natural log of the absolute value of x minus 1. And if it really bothers you that we have a fraction within a fraction, we multiply by 3 and multiply by 3. So the cleanest version of this would be 3 over 1 minus 3 natural log of the absolute value of x minus 1, which is kind of a strange answer. Now, we also need to consider our domain. We have a natural log in this problem. We also had a denominator, right? So looking at this part right here, which was 1 over y, we know that y has to either be bigger than 0 or less than 0. Well, based on our initial point, we had 3, so we know our y values are greater than 0. But we also consider, so that was our range that we're really considering, we also consider this. So in differential equations, when we have our slope fields, we can only have one piece to the curve. So let's say it was undefined in the middle. Maybe this is part of my curve. I can't have this also as my solution and have an asymptote or something between them. I can't have two branches, we call it. So we have to pick one of the two sides. So the only x value we can't have is x equals 1. It makes it undefined. And we noticed that even from our slope fields, right? We couldn't have x equals 1. Okay, so we know x can't be 1, so x must be bigger than 1, or x must be smaller than 1. So we go back here and we look at our x value. Well, x is equal to 2. So that means that x must be bigger than 1. So that's our domain. So we're going to say that x has to be bigger than 1. But this one also has kind of a weird domain because we have a denominator in our final solution. So we didn't do a lot of these in class. So luckily, if you notice in the instructions, this one they did not give you a point for the domain. But really, technically, the domain is that this 1 minus 3 natural log of x minus 1, it can't be equal to 0. Okay, so we add the 3, I'll just put can't be equal to 0. I add that 3 natural log of x plus 1 over, I divide by 3, and then I do e raised to both sides. So that cancels. So I get x minus 1 can't be e to the 1/3. And you can do the plus or minus and so on. It actually ends up being a parenthesis because our x values had to be bigger than 1 right here, right? So x had to be bigger than 1. So we're going to kind of cheat a little bit and put a parenthesis. And then we're going to add the 1 over. So it's going to be 1 plus e to the 1/3 can't be x. Okay, so that's a number that's bigger than 1. So what our domain ends up being is 1 is the smallest that it could possibly be, and 1 plus e to the 1/3, or the cube root of e if you want, is the biggest that it can be, which is kind of a crazy domain. So I don't know. I liked that question though. Tricky, tricky, tricky. All right, so let's look at our graph, or our answers. So you got 2 points for having the zero slopes for these two, and 1 point for the zero slopes, and you got 1 point for the non-zero slopes. For part B, we got 1 point for a tangent line, and 1 point for our approximation, which was 3.9. And for part C, like always, you get 0 points if you forget the step where you separate your variables. But if you remember that, you have an opportunity to get up to 5 points. So we separated our variables, so we had a check mark there. We got this antiderivative and this antiderivative, so we got 2 check marks there. We remember that we had a plus c. We used the initial condition as well for that other part of that point, and then we solved for y. And notice they just left the 1/3 in the answer. So sometimes if you think, oh my gosh, I don't think I simplified completely, they're going to count it wrong. They're not going to count it wrong. They're not going to look for every single simplification step. Just try your best and at least get y equals, right? But you could have things that aren't totally simplified on the other side. And then they did say, note the solution is valid, but they didn't give us any points for getting that right. Wouldn't that be nice if they gave bonus points? I think that's what they should have done, for sure, right? 2016, number 5, says the inside of a funnel of height 10 inches has a circular cross-section as shown in the figure above. At height h, the radius of the funnel is given by r equals 1/20 times 3 plus h squared, where h is between 0 and 10. The units of r and h are in inches. Find the average value of the radius of the funnel. So we know when we see average value of a function that we do 1/b minus a, the integral from a to b of f of x dx. So we're finding the average value of the radius. That means that we're going to do 1/10 minus 0, the integral from 0 to 10 of 1/20, 3 plus h squared, dh in this case. All right, and this is a non-calculator question. I know you guys are crying. You want to use Math 9 so much, but we have to do this by hand. Okay, so we're going to have the 1/10 out front, and we're also going to pull that 1/20 out front. And then we have the integral from 0 to 10 of 3 plus h squared dh. So it's really not too bad. So we have 1/200. And when we integrate 3, we get 3h. When we integrate h squared, we get 1/3 of h cubed. And we're going from 0 to 10. So we have 1/200 just out front. And then we plug in the 10, so we get 30 plus 1/3 of 10 times 10 times 10. So 1,000. And then the second part is just 0, luckily. So we get 1/200 times 30 plus 1,000/3, which is, you could write as 333.333 if you want. So you could also just get common denominators. Personally, I think that's a little bit easier because we're going to divide by 200. So maybe let's write this as 1,000/3. And let's write the 30 as 90/3. So we get 1,090/3 times that 200, so I'm going to say 600, which will reduce out by 10. So we get 109/60. Now what this was the average value of the radius, and our radius was in terms of inches. So don't forget your units. A lot of times you get 1 point just for your units. So we have 109/60 inches, and we'll leave it like that. You don't have to find a decimal approximation or anything because it's a non-calculator section. All right, part B. So find the volume of the funnel. All right, so when we find the volume of the funnel, what we're doing is we have circular cross sections. And we're basically just using our knowledge of volume. We're going to find the areas of all of these circles, and we're going to integrate it from a height of 0 to a height of 10. Okay, so we're going to integrate, and we're going to have pi r squared for the areas of each cross section. Well, we were given r, right? So it's 1/20, and then we have 3 plus h squared, and we square it. And this is from 0 to 10. So they are truly testing whether you are able to integrate by hand, because you actually have to do this by hand. So painful. So we're going to pull out, let's see, the 1/20, we're going to square that. So I'm going to have pi, and then I'm going to have times 1/400. And I'm going to FOIL the 3 plus h squared out. So I'm going to have 9 plus 6h squared plus h to the 4th. And I have to integrate this. So I have pi/400, and I have the integral from 0, well, let's go ahead and integrate. So I get 9h plus 2h cubed plus h to the 5th with a 1/5 out front, so h to the 5th over 5 I could write from 0 to 10, and I continue to find it. And if you're running out of time on your AP test, it's fine. Like you can just do, you're probably gonna miss 1 point for not getting this totally simplified. So I'm plugging in 100, so I'm gonna get 2,000, or not 100, 10, so I get 2,000. And I'm plugging in 10 here, so I get, oh man, 10, I'm gonna have 5 zeros, so 100,000 divided by 5, so I get 20,000, like that. And then the rest was minus 0. So again, combine your like terms. So we get 22,090 pi over 400. Now, do I think they're going to care too much if you simplify? No, but at least divide by 10, right? See that? And I think that's actually as far down as it goes, actually. So it's like that. All right, so part C says the funnel contains liquid that is draining from the very bottom. At the instant when the height of the liquid is h equals 3 inches, the radius of the surface of the liquid is decreasing at a rate of 1/5 inch per second. At this instant, what is the rate of change of the height of the liquid with respect to time? Okay, everything about this problem should be screaming at you. It's a related rates problem. Okay, so if you notice it says, at the instant when the height is this, and it says with respect to time, so that's like dt, and then it says inches per second, right? These are all clues that it's related rates. So we set it up. And we say, okay, well, let's see. The radius of the surface of the liquid is decreasing, so negative 1/5. Let's write down what we know. And we're trying to find dH over dt is equal to something when h is equal to 3. Okay, so let's write down kind of our background knowledge. Okay, so we need to figure out some kind of relationship between our radius and our height. So if we go back here, it's not quite like the cone problems we did, but similar. So we don't have like a similar triangle we're setting it up with, but we do have this relationship. So we know that r is equal to 1/20 times 3 plus h squared. So we're going to use that. Remember, it's called related rates. If we can find something that helps us relate our two values, we're good to go. And we're going to take the derivative. So I'm going to say dr over dt is equal to, kind of like product rule, 1/20 times the derivative of 3 plus h squared, which is 2h times dh over dt. And then the derivative of 1/20 is now 0, so the second part's gone. And we start reducing, so we're like, okay, that's 10, that's 1. We said at the instant when the height was equal to 3, we're finding dH over dt, and dr over dt is negative 1/5. So when we divide it over, we get dH over dt is negative 1/15. So the question said, at what is the rate of change of the height of the liquid with respect to time? So you could say, I forgot my 10, didn't I? Hang on. 3/10, is that what it was? 3/10. And then I'm going to multiply that over. So negative 2/3, sorry. I looked at the key really quickly and saw I got it wrong. All right, and that's in inches per second. All right, so what was I saying here? So if we describe this out, if we wrote it in words, we would say the height is decreasing at a rate of 2/3 inches per second. But be careful, if you say the height is decreasing and then you do a negative, that's like a double negative in math, so we don't do that. So you could just use a general word like the height is changing at a rate of negative 2/3 inches per second. You could do that as well. All right, so let's see the scoring for this question. So part A, we got 1 point for the integral, so having this part set up, 1 point for the antiderivative and 1 point for our answer. For part B, we got 1 point for the integrand, 1 point for the antiderivative, 1 point for the answer, and 2 points for our chain rule. So I'm guessing the dH over dt and that part I'm guessing. and 1 point for our answer. A lot of times it does say answer with units, so be careful, just make sure that you have your units on that. Last question, 2016 number 6, is one of the chart problems. So it says the function f and g have continuous second derivatives. The table gives values for the functions and their derivatives at selected values of x. So part A says let k of x equal f of g of x. Write an equation for the tangent line. So we know when we're finding a tangent line, we find both the slope and the point. So we need to find k prime of x to find the slope. And this derivative of f of g of x is going to be f prime of the inside times the derivative of the inside. That is the chain rule. So the example I always give you is sine of something like x squared or 2x or whatever. Its derivative is cosine, so that's our outer function, but we keep the inside the same, and then we multiply by the derivative of the inside. We've done that many, many times. All right, so if I'm finding k prime of 3, that's going to be the slope for my tangent line. And that's going to be f prime of g of 3 times g prime of 3. We did this one, something similar to this the other day where we had to keep looking at the chart. So g of 3 is 6 times g prime of 3 is 2. F prime of 6 is 5. So we get a total of 10 for the slope. And then our point is 3 comma something. So basically we just need to find k of 3, which is still just f of g of 3. So g of 3 is 6, and f of 6 is 4. Lots of places where you can make mistakes, right? So we have y minus 4 equals m, which was 10, times x minus 3 is the equation of that tangent line. All right, now part B says let h of x equal g of x over f of x. Now be careful, a lot of times we did f of x over g of x, so it's not quite the quotient rule we're used to seeing in textbooks, but it's still the quotient rule. So we're going to do h prime of x is equal to low, which is f of x, d high is g prime of x, minus high d low. So high is g of x, d low is f prime of x, all over the square of what's below. So all over f of x quantity squared. So we're finding h prime of 1. So again, lots of places where we can make mistakes. So we're going to find f of 1, which is negative 6, times g prime of 1, which is 8, minus g of 1, which is 2, times f prime of 1, which is 3, all over f of 1, which is negative 6 squared. So we're going to get negative 48 minus 6 all over 36. So we get negative 54 over 36, which reduces by 9. So divide by 9 on the top and bottom. So we get negative 6 over 4. So actually we can go by 18 actually. So negative 3 over 2 is the answer. All right, so then part C, the last part, sorry, I'm kind of writing this all over the place, says evaluate the integral from 1 to 3 of f double prime of 2x dx. And this, from what I hear, was the most missed problem last year. Because what students did is they forgot that if you have like f of 2x or even f double prime of 2x, it involves a u substitution. So what we need to do is write u is equal to 2x, because then du is equal to 2 dx. So we're gaining a 1/2 in the front of our integral. So it should look like f double prime of u du with a 1/2. And then those x values, 1 to 3, let's change those to u's. So if we have u of 1 and u of 3, u of 1 becomes 2 from this equation right here, and u of 3 becomes 6. So I'm going from 2 on the bottom to 6 on top. Now we can integrate. We know how to integrate f double prime. We know that it's f prime. But like I said, a lot of students forgot that 1/2 out front. So I'm going to get f prime of u, and that's going to go from 2 to 6. So it's going to be 1/2 of f prime of 6 minus f prime of 2. So it's 1/2, and then we go back to the table, and we find f prime of 6 and f prime of 2. So f prime of 6, clear these out of here, f prime of 6 is 5, and f prime of 2 is negative 2. So we have 5 minus a negative 2, which becomes 7, so our answer should be 7 over 2. So really quickly, the scoring, if you look at it, you got 3 points for part A, which I feel like was not too demanding. I think you guys know how to do that. So you get 2 points for finding the slope correctly at x equals 3, so getting that 10. Probably involves the chain rule for one of the points, and then the final answer, I would guess. And 1 point for your equation of the tangent line, which ours was y minus 4 equals 10 times x minus 3, so we're good. 3 points for the next part, so you got 2 points for finding h prime of 1 correctly, so probably for the setup and that answer of negative 3 over, well, I guess it just said the expression, right? So you got 3 points for this. So, 1 point here, 1 point here, and I don't know where they got the other point, so. And then part C, 2 points for the antiderivative, so probably knowing that you had a u substitution, so having that 1/2, and then knowing it's f prime of 2x or f prime of u if you changed it. And then 1 point for the answer of 7 over 2. So it's kind of funny that this is a question 6 because I know that you guys can all do this question, and you could even get all 9 points. So it's a good way to end this 2016 exam. Good luck on your exam. I'm very excited to see how you all will do.